So let's get started with a definition of what 1 radian is. If you take a circle, and you take the length of the radius and you wrap it along the edge of the circle, you'll form an arc length, what we call an arc length, that's 1 radius long. So if I have this circle with that radius, that angle there is going to be 1 radian if the length of that arc, or the length of the path along the circumference of the circle, is 1 radius. And it doesn't matter whether this is a circle with a radius of 2 centimeters, where this r would be 2, this r would be 2, and that r would be 2. That angle is 1 radian. So you want to be careful with the language. 1 radian is the angle created or subtended by an arc length equal to 1 radius. And it turns out, and I used to spend time explaining this, I would be happy to explain it later to you, but it turns out it's not that important why this is the case. I don't think. That if I asked you how many radians is 180 degrees, so if you look at my arm, and I'm going to be using this kind of modeling a lot in this unit, from here in a counterclockwise direction, 180 degrees is that, right? We should be familiar with what 180 degrees is. Well, it turns out that you can fit 3 of these radii and a little bit more. It turns out that the number of radiuses, or radii, you can fit on half of a circle is exactly equal to pi. And this is something that is non-negotiable. That is a fact. That's like knowing 2 times 3 is 6. You cannot, from this point forward, say, how many radians is 180 degrees? It's just something you need to know. Visually, this is what we're talking about. I'll play this through a couple times so you can think about it. Of course, I hope you know pi is equal to approximately 3.14. It has something to do with the fact, everybody, that a circumference of a circle is found by taking 2 times pi times the radius. And you can set up ratios with arc lengths and angles to prove that pi radians is 180 degrees. And at the very end of this, I think you saw, maybe you didn't because I was talking, you might have been looking at me, that 2 pi radians, which is a full revolution, is 360 degrees. I'll just let it run through one more time. It'll only take a second. So that's 3 radians. That little bit extra is that 0.1415926. And of course, if that's pi radians to there, if you go all the way around, that's 2 pi radians. So complete the following chart using the above information. When we write an angle in degrees, you have to put that degree symbol. When you write an angle in radians, you do not have to put any units in math. So 0 degrees is 0 radians. Can you write instead that? Yes. RAD is the way we abbreviate radians. You could write 0 radians and just write the whole word out. It doesn't really matter. But just because of the space I have in the table, I'm not going to write rad, and we don't need to anyway. So in Math 20, everybody, you talk a lot about 30 degrees and 45 degrees and 60 degrees as being special angles. And there are, how many of you have a faint memory of special triangles that have 45-degree angles and 60-degree angles and 30-degree angles? Not all in one triangle. Well, when we talk about the unit circle on Friday, we're going to be referring to those special triangles. 30 degrees, 45, 60, 90, and 180, and 360, I suppose, are all special because they divide evenly without remainder into a full revolution and half a revolution. So for example, if I were to take this 180-degree slice here and cut it so I had 90-degree slices, how many 90-degree slices would I have? Well, 2, right? I could take this and I could cut it down the center, and I get 2 pieces. Well, listen, if that whole thing is pi, not pie that you eat, pi, then each of those is pi over 2. Each of those is half pi, which means 90 degrees is pi over 2 rads. And that's another fact. That's something that sooner or later you're not going to have to reason it out. You're just going to say, oh yeah, pi over 2 is 90. If I were to instead break this into 45-degree chunks, can you live with that? That's not, I have difficulty with 45 degrees. A little bit less. I mean, don't worry about drawing this perfectly. I just want it to look right here. I also have another division that I can make over here. If I were to take that 180 degrees and divide it into 45-degree chunks, 45, 90, 135, 180, I'm splitting that region into 4 pieces, which means each of those is a quarter of 180 degrees, which means each of those is a quarter of pi. Knowing this translation is important, that you can think degrees, radians, radians, degrees. On the other hand, and I'll use a different color here, I can take this and I can split it into 30-degree chunks. Now let me model this first. 30 degrees. Here's the center of the rotation. 30, 60, 90, 120, 150, 180. So in 90 degrees, there's 3 30-degree chunks. So if I break up this entire section into 30-degree chunks, I suppose I could get my protractor out. That doesn't look quite right. I think this needs to go up a bit. Maybe. You get the idea here? I have one more I can put here. 30, 60, 90, 120, 150, 180. So how many 30-degree chunks are there in 180? 6. That means each of these 30-degree chunks is 1/6 of pi radians, because pi is 180. And this is what I want you to continually be doing, is thinking in terms of pieces and the rotation. And you're looking at it from the proper perspective. We're going to be rotating counterclockwise all the time, and I will be showing you what you would see if you did this. 60 degrees, well, there's a 60-degree chunk from here to there. There's another one, and there's another one. There's only 3 60-degree chunks in 180. So 60 degrees is pi over 3. Of course, 180 is pi, and 360 is 2 pi. Are you picking up? Yeah.
We also have a 270 degree.
You also have a 270. That's good, because I meant to include 270. And you will have the 270 between the 180 and the 360. Thank you, Armand. How many radians would 270 degrees be? Well, there's a lot of ways to figure it out, but if you watch my arm, there's one 90, there's a second 90, there's a third 90. 90 is pi over 2, so that's 1, 2, 3 pi over 2. And again, you want to think in terms of chunks. Thank you for that. So this is 3 pi over 2. Are we okay with that? Any questions? So we're going to be doing, as I said, a lot of review with Math 20. In Math 20, we have a very special way of defining a rotation angle. You understand, of course, from Math 20 that trigonometry extends way beyond triangles. It extends to the concept of rotations. And a rotation angle theta is formed whenever you take an initial arm and you rotate it around or about a fixed point. So this is a rotation angle. But so that we're all speaking the same language, there's a standard way of doing this. If the vertex is at the origin and the initial arm lies along the positive x-axis, then we say that the rotation angle is in standard position. This shows a rotation angle theta in standard position. And I hope that you remember from last year or last course that positive rotation angles are counterclockwise. And I know that that seems non-intuitive. It seems as though positive should be clockwise. The reason why positive rotations are counterclockwise, which means if you watch the second hand of the clock, it's rotating this way, that's clockwise. When it goes the other way, that's counterclockwise. The reason for that is then you sweep out, starting at 0, the quadrants in the proper order. You go through quadrant 1, then quadrant 2, then quadrant 3, then quadrant 4. So I'm going to give you a little handout here. It's just a single sheet called Common Rotation Angles. And we need to become intimately familiar with all of these angles in both degrees and radians. And once you get the gist of things, as my dad would say, you will probably discover that thinking in radians is easier than thinking in degrees. I hope. So what are we asked to do here? We are asked on this diagram, and you can see a whole bunch of points there, right? We are asked to, starting with a rotation angle of 0 degrees, which is 0 radians, we are asked to label the rotation angles that would correspond to all of these dots going in one full positive rotation. So we're starting here, and we're going counterclockwise all around. Then in a second, we'll do the bottom. Okay, I just want it a little bit larger here. So we need to label these. Well, this is pretty easy. We have to label it in degrees and radians, so you have to make a decision where you're going to write the degrees and write the radians. I'm going to go ahead and write the degrees inside. Whoops. I'm going to go ahead and write the degrees inside, so it's 0 degrees. And then over here, I'm going to put 0 rads. And again, I could put 0 RAD, but I don't need to. That's why I've been picky with you if you had me for Math 20. When you wrote an angle in degrees, if you didn't put the degree symbol, I'd kind of go, no, you need a degree symbol. So this is how I do it. I mean, it's hard for me to not use my experience here. I know this is pi over 6. I know 30 degrees is pi over 6. But you don't have to start there. You could start at the top, and everybody here should know that the top is 90 degrees. But you should know that it's pi over 2. If you don't already, then I suppose you can start over here and say this is 180 degrees, and you have to know 180 is pi. You have to have some frame of reference, something you're starting with so that you can work with. By the way, you want to see that vein in my forehead start to throb? Go ahead and write that. In other words, don't write fractions that way in high school math. Write them as a numerator over a denominator. I'm not going to have an aneurysm because of it. I'll just remind you. Don't do that, okay? So what else could you do? You could say, well, this is 45 degrees. This is 45 degrees. And that's a quarter of pi. It's pi over 4. Now, just bear with me here. I know that you could probably do this whole thing. But if I asked you to fill in the number of degrees here, my experience is it's going to take you longer to figure that out than to figure out how many radians it is. Because when I look at radians, all I do is I say, this is, whoops, I did say pi over 4, I believe. I just wrote pi over 2 by mistake. This is 1 pi over 4. So from here to here is 1 pi over 4. Well, that means this is 2 pi over 4. Oh, wait a minute, just a second here. 2 pi over 4. Oh, that's pi over 2. Right, we already have that. But that makes this 3 pi over 4. I don't need to go 180 minus 45 or 90 plus 45. I can just say, look at my arm. 1, 2, 3 pi over 4. Just going along with that, and I'll write that down in a second, if I said, what is this? Well, that's a 45 degree kind of chunk. So if you look at my arm, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4. That's 7 pi over 4. I don't need to subtract anything or add anything. I count. We can put it here now if you want. Let's go back to quadrants 1 and 2. So this is 3 pi over 4. See, now I have to do a bit more thinking. In my mind, I have to do more thinking to find out how many degrees that is. I mean, I've done it enough that I know it's 135. And I know I'm dancing all over the place here. I'm going with the pi over 4s and the pi over 2s. It doesn't really matter. We could do the pi over 6s now. That's 1 pi over 6, 2 pi over 6, 3 pi over 6, which is pi over 2. 3 over 6 is 1 over 2. 4 pi over 6, 5 pi over 6, 6 pi over 6. So this is 4 pi over 6 right here. Let's see, 4 pi over 6. Well, that's 2 pi over 3. Which we could have counted off in pi over 3s. I could have said that this is 1 pi over 3, 2 pi over 3. Oh, I could have done it that way. Speaking of which, this is 2 pi over 3. And again, this is 5 pi over 6. Why is it 5 pi over 6? Well, look at my arm. 1, 2, 3, 4, 5 pi over 6. And I hope you're starting to gain an appreciation, and this is pi over 6, for what I said a few minutes ago, which is that you could probably write the angles in radians quicker than you can do it in degrees. But you do need to know that this 30 degrees is pi over 6, the 45 is pi over 4, the 60 is pi over 3. We can fill these in though. 30 degrees, 60 degrees, 90 plus another 30 is 120 degrees. 120 plus another 30 is 150 degrees. And then, of course, 180 down there. Have we got them all? We've got them all. So as I said, you need to be intimately familiar with this. Let's continue into, yeah? Thank you, Paige. It's just pi over 3. Yeah. I think why I had the 2 there is I was counting in pi over 6s, and I said 2 pi over 6. But what I should have said is, yes, 2 pi over 6 is 1 pi over 3. Are we okay with that? Okay, let's just continue. Speaking of the pi over 6s, this point right here, which we've already labeled, this is 0 degrees pi rads. That's pi radians, which is 6 pi over 6. So this would be 7 pi over 6. This point here would be 8 pi over 6. 8 pi over 6. Well, 8 over 6, and if you have to write down 8 over 6 to see this, then that's fine. It's 4 over 3. So this is 4 pi over 3, which you certainly could have arrived at by looking at it this way. Pi over 3 is 60. 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. And when I say 60, if you look at my arm, I purposefully probably make it bigger than 60 because I don't want you to think that I'm talking about that 45. I want to make it very clear that I'm talking about the one that's closer to the y-axis than the x-axis. So going back to the 7 pi over 6, this was 7 pi over 6, 8 pi over 6, 9 pi over 6. 9 over 6 is 3 over 2. So this is 3 pi over 2. That's 9 pi over 6. 10 pi over 6. What's 10 over 6? 5 over 3. So this becomes 5 pi over 3, which, again, you could have done by doing this. 1, 2, 3, 4, 5 pi over 3. So this is 10 pi over 6, making this next 30-degree chunk 11 pi over 6. We were asked to go back to the beginning here. So you had 0 degrees and 0 rads. We could put 360 degrees and 2 pi rads. And now we'll just take a minute and fill in the degrees. Oh, I'm missing one here. This one right here. Well, that's a pi over 4 chunk. 1, 2, 3, 4, 5, 6, 5 pi over 4s. There's other reasons that we want to use radians other than the fact that it's easier to locate these positions, I think, in radians. We'll get to that in the units. So this is 210 degrees. This is 180 plus 45, which is 225. This one is 180 plus 60, which is 240, 270, 300, 330. And I think, whoops. And I think 315 degrees. This exercise, thank you, this exercise is not just so that you have some template to look at. Hopefully at this point in time, you can take that template and throw it out, right? It's a learning exercise. I'm not saying throw it out. Hang on to it in case you absolutely need it as a study guide, but within a few days, you should not need to refer to this sheet of paper at all. All right. Let's convert now. This is the next part of the lesson where we are converting between degrees and radians. How many radians is 75 degrees? Well, unfortunately, 75 degrees is not a special angle. In other words, 180 is not a multiple of 75. Not like 30 or 45 or 60. So the best advice here would be to use a ratio. That to say pi rads over 180 degrees has to be constant. That's how ratios work. If I said how many rads is 360, you'd say 2 pi. And if you take 2 pi divided by 360, you get the same thing as pi divided by 180. So all we're doing here is we're setting up a ratio, and we're solving that for x. Now I put the units in here just to demonstrate to you that the units will be radians because the degree symbols will cancel and we'll be left with rads. So x is equal to 75 pi over 180. And we want this simplified. So I'm going to do something on my calculator, which is kind of silly. I'm going to take 75 times pi divided by 180. So the number of radians is approximately 1.3 radians. But if I want an exact value, and I want to convert this to an exact value, why, when I go math, enter, enter, can my calculator not convert it to an exact value? Liberty?
Because we use pi and it goes on forever.
Right. Pi goes on forever in terms of decimals. Pi is an irrational number. You're not going to get a rational number out of pi. But what we can do, I would argue that you should be able to simplify it anyway, is just ignore the pi and see that the 75 over 180 is 5 over 12, which means that the exact value for this rotation angle is 5 pi over 12 rads. Now, I will admit that when we draw the rotation angle, we're probably going to think of degrees. 75 degrees, we know what 75 degrees looks like. And whether you write theta equals 75 or theta equals 5 pi over 12, that's your choice. We are asked to give an exact value. This is the exact value. And we are also asked to give a decimal approximation to 1 decimal place. Well, that's what I got. That's what I got, everybody. When I take 75 times pi over 180. So pi is not a variable. Pi is a number. It's not even a parameter. Pi is a number. So it's about 1.3. And I don't need to write the word rad. Any question with A here? All right, what about negative 120? Well, let's sketch it first. Negative 120 is 2 negative 60s. Right, so I'm thinking, if you look at my arm, negative 1, negative 2. Negative 120 is going to be over here. Ish. And we should label this. Of course, it's going in a clockwise direction because the rotation angle is negative. Do you need to set up a ratio to convert this to radians? No. You could, and I will show that to you. But 120 degrees is 2 pi over 3s. It's 2 of those pi over 3 wedges. It happens to be in a negative direction, but the 120 itself is 2 pi over 3. So we can just write negative 2 pi over 3. Could you, and that's rads, could you have done what we did in the first example? Pi over 180 degrees equals x over negative 120. Sure. X will be negative 120 pi over 180. But guess what negative 120 over 180 is? Negative 2 over 3, right? We should have a decimal approximation here as well. And that just means we're literally going to our calculator and saying negative 2 pi divided by 3. I'm getting about negative 2.1 rads. You in agreement? Good? Any questions with that one? Right. How do you convert now? We're going to go in the other direction, say radians to degrees. Well, you do not want to set up a ratio here. You can. It just gets ugly and it gets messy when it doesn't need to be. How many degrees is pi radians? Listen to that question. How many degrees is pi radians? 180. Forget about this. Pi radians is 180. So this is that many degrees. If it's 3/4 of pi and pi is 180, we just need to figure out what 3/4 of 180 is. And by the way, when you sketch it, again, I think it's easier to sketch by looking at the radian measure. Oops. Is that 135? So 135 degrees. There's no necessity here to me talk about decimal approximations because it's exactly 135. I want to take this opportunity to point out to you, and it may seem unimportant, but it's crucial, that every rotation angle I've drawn has an arrowhead not on the x-axis, away from the x-axis. You would never do this for a rotation angle, just in case anybody is. Let's take a look at the next one, B. Well, again, just take negative 11 times 180 over 16. Right? 180 degrees is pi radians. So negative 11 times 180 degrees over 16. Help. What'd you get?
I didn't do it yet.
You didn't do it yet? Have you got a page? Negative 123? That's fine. I could have been way off. I think I was way off. I know what I was doing. Negative 123? Oh, yours just says 6. Gotcha. You don't have a 16 there? It's just 6? Oh, okay. Try that again. You will get negative 330, I think. Yeah. And you could have, let's see, negative 330. You could have done this if you look up here. This is pi over 6. Negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You could have reasoned out that it's negative 330 that way and drawn it. So negative 330. And the final one, I think here, does yours say 6.5 in light of the last one? Okay. 6.5 what? Radians, right? There's no degree symbol, it's radians. So we do have to use a ratio here. And I don't know if this has been taught to you specifically, but when you're using a ratio, the best advice is to set up your ratio so your unknown is going to be on the top. Right? We're trying to find degrees, so why don't you put 180 degrees over pi and go x over 6.5. So we multiply 180 by 6.5. For some reason, I want to say 1140. Nope. 1170? Rats. You get 1170. You have a degree symbol, and it's over pi. So this brings up an interesting point that most people, after this lesson, they see the symbol pi and they think they're talking about radians. We're not. The exact value of the degrees just happens to be a number that contains reference to pi. If you want to know what the decimal approximation is, you can take 1170 over pi. 372.4 degrees. Are we okay with C? So where are we at so far? You need to be familiar with all those special angles. You need to be able to convert degrees to radians, radians to degrees, as exact values or decimal values, and you need to be able to sketch rotation angles. There's one little cherry we're going to put on the top of this. And it has to do with what's called coterminality. Coterminal angles are different angles that have the same terminal arm. They are different journeys that end up in the same location. The angle is the journey. The terminal arm is the destination. That's why when your plane lands at the airport, it taxis to the terminal. It's where you end your journey. So for example, 50 degrees and 410 are coterminal. Just think about these numbers for a second. 410 degrees, if I said rotate 410, you'd say, well, that's more than 360. How many degrees more than 360 is 410? 50. So I can either land here by doing this, or I can land here by doing that. You get the idea here? So sketch a rotation angle of 60 degrees. Like stealing candy from a tired baby. Pretty simple. You don't need to get a protractor out, although for exams you are allowed a protractor. So for written responses, precision is better. What are two angles that are coterminal with 60? And I'm going to give you this condition. I want a positive angle that's coterminal with 60, and I want a negative angle that's coterminal with 60. So take a minute and determine a positive and a negative angle that are each coterminal with 60 degrees. And my guess would be that those are the angles most students will write. Because they will say, to go from this location back to this location, I can add a full revolution, so I'm going to add 360. And I'm going to go out on a limb here and say, those of you that thought of how to get negative 300, you probably said, what do I have to rotate in a negative direction to get there? Am I right? But I want you to notice something. Take your calculator and take 60 plus 360. You get 420. Take your calculator and take 60 minus 360. We get negative 300. What we're doing is we're taking the angle that we're given and we're adding a full revolution to get back there, or we're taking away a full revolution. Could I say that a coterminal angle will be that? Is that going to be coterminal? Well, yeah, because I'm saying start at 60 degrees and go in a clockwise direction 14 times. Right? So I could do that. If I wanted to be cheeky about it, I could say 60 minus 14 times 360. It doesn't matter. There's an infinite number of answers. Of course, figuring out that that is coterminal after the fact is a little tricky. Negative 275. Well, negative 275, if we want to sketch it, that's negative 270. Negative 275 is just a sliver more. You do not want to put your arrow here, because that's not what we drew. We drew negative 275. I'm leading up to something here, and I want you to follow along on your calculator or follow along up here. I'm going to put in for y1 negative 275 plus $360x. And I'm going to set up my calculator in the table settings to start at 0 and go up by 1 automatically. What is this? Did I go times? Thank you, Armand. I'm going to set up my calculator, start at 0 and go up by 1 automatically. What this means is the first entry is what that angle is when I don't add any 360s. The second one is what happens when I add one 360, which is a full revolution. In other words, 85 is coterminal. I'm just taking all the heavy lifting out of it. When x is 2, I'm taking the negative 275 and I'm adding two 360s, 2 times 360, which is 2 full revolutions. So these are all coterminal angles. And if I scroll upwards, I get other coterminal angles because then I'm getting into the negative rotations. It's just a quick way for you to check to see if an angle is coterminal or not. So you can choose to write down whatever you like here. I'm asking you to come up with one positive and one negative. So well, do whatever you want, right? There's lots of them you can use. You don't have to think about the rotations to get them. It's a mathematical process of adding and subtracting multiples of a full revolution. Sketch a rotation angle of 5 pi over 6. So how many of you, I'm going to give you 5 seconds to think about 5 pi over 6. How many of you know that it's here? That's the goal. You should know that it's there. 1, 2, 3, 4, 5 pi over 6. Now, how do we get coterminal angles? I would not recommend converting this to degrees to find coterminal angles and then converting the coterminal angles back to rads. That's a bad mistake. What do we add to a rotation angle to get back to the rotation angle, back to that location? We add a full revolution. So we have to add 2 pi. But instead of saying, let's add 2 pi, why don't we add 12 pi over 6s? Because 12 pi over 6s is a full revolution. And some of you will know 12 pi over 6 is a full revolution because you will convert the 2 over 1 to 12 over 6. How many of you get that? How many of you know it's 12 pi over 6 just because that's how many pi over 6s there are in the full revolution? You might know that as well. So, 17 pi over 6. Add another 12 pi over 6. Would be 29 pi over 6. I could continue doing this. Or I could take away 12 pi over 6. So I could go 5 minus 12 is negative 7. So negative 7 pi over 6. If you wanted to keep going, the next one would be negative 19 pi over 6. Are you with me on that? Negative 3 pi over 4. Man, it's hard for me. I know I put a lot of pressure on you guys as students, but you should know, and I just can't draw 45-degree angles. There's some part of my brain there's just a vacuous space in that part of my brain. You should know this is negative 3 pi over 4. You should. Negative 1, 2, 3 pi over 4. So what are we going to do to that to get coterminal angles? We're going to add or subtract (8 pi over 4). because 8 over 4 is 2, which is a full revolution in terms of pi. So negative 3 plus 8 would be 5 pi over 4. Negative 3 minus 8 would be negative 11 pi over 4. And that's 2. But you could keep adding 8 pi over 4 and keep taking away 8 pi over 4. Does that make sense? So that's the additional point here, but then there's one other, but that cherry on top, now I'm just going to cover it with whipped cream. There's one other thing we need to know. And it's how to write a general form statement for coterminal angles. Would you agree that when we go back to, it doesn't matter which one, this question, I've written 2 coterminal angles here out of an infinite number of coterminal angles? What a general statement is a statement telling us the infinite number, every coterminal angle. Clearly there has to be a shortcut way of writing it. You're not going to sit there till the end of time writing down angles, right? But it's pretty simple. If I told you that we had an angle that was 130 degrees, what's a statement for all the coterminal angles? And I'm going to get to the goofy wording here in a second. The answer is all of the coterminal angles will be 130 degrees plus 360 degrees times n, where n has to be a certain type of number. The number it needs to be is an integer. What are integers? 0, plus or minus 1, plus or minus 2, plus or minus 3. So that plus or minus 1, plus or minus 2, plus or minus 3 is going to add 1 or take away 1 full revolution. Add 2 or take away 2 full revolutions. And the n equals 0 will give you the original 130. And that's why I said up here, express the angles coterminal with and including 130. Because if I don't include 130, I can't say n is an integer. I have to be sneaky, but I don't want to go there. The coterminal angles here will be 7 pi over 3 plus 2 pi n, where n is an element of the integers. I want to just show you one final thing here. I don't think you really are going to encounter this, but you never know. I'm going to talk about that 130 degree one. So we said the coterminal angles are 130 degrees plus 360 degrees n, where n is an integer. And the fact that n is an integer has the plus or minus involved, so we don't need to put plus or minus, and it has the 0, which is what we were asked for. Could I write this instead? So I'm saying, now I'm going plus or minus those multiples of the revolution, where n is a whole number. I could do that, because whole numbers are 0, which we include, 1, 2, 3, and the plus or minus now is necessary. Could I write this? Could I say n is a natural number, not a whole number? Why not? It's not that. Liberty, do you know? Jackson?
It might not end up being a full rotation, and then it wouldn't be coterminal anymore.
These will be for full rotations. Natural numbers are 1, 2, 3, 4. There's no decimals here.
You're not taking into account the 130 degrees?
Right. This doesn't include 0. 0 is not a natural number. Remember what I've said? Whole numbers, there's a whole. 0. Whole numbers include 0. Natural numbers do not. So these include 130 degrees. This does not include 130 degrees. So I'm being very technical here, mainly for my Math 31 students in calculus, but if you were asked for mathematically a statement for the coterminal angles, this is the way to go. But if you're asked for the coterminal angles that also include the original angle, you have to do one of the others. All right? So a lot of little bits and pieces here today. You need to know all of these common angles. Just in a blink of an eye, you should know them. And you need to understand the principle of coterminal angles. And I'm assuming here that you've carried forward your work from Math 20, that you understand about positive rotations, negative rotations, all of that. And you also need to be able to convert, it's over here, degrees to radians, exact values or decimal values. And all of this is just pouring the concrete for the building that we're creating here for this unit. It's just the start. So you can see what the assignment is, questions 1 to 10 on page 4 and 5 of that unit handout. You got a fair amount of time here. You have about 20 minutes left. Get started. I'll come around and I'll give you a hand in just a few minutes. I want to take care of attendance and a couple of other things.